Hello everyone. Welcome to the class of Discrete Mathematical Structures. Today I'll be teaching a topic in relations and functions, and the topic name is Invertible Functions. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. First, let us know the definition of invertible functions. A function f from a to b is said to be invertible if there exists a function g from b to a such that g composition f is equal to I a and f composition g is equal to I b, where IA is the identity function on A and IB denotes the identity function on B. Then G is called the inverse of F, and we write this expression as G is equal to F inverse. So in order to say a function is invertible function, there exists another function G from B to A given the function F from A to B such that G composition F and F composition G should be defined as IA and IB, where IA and IB are the identity functions on A and B respectively. If such case is happening, then we can say that G is called the inverse of F and symbolically it is written as G equal to F inverse. Let us note the following points. If a function f from a to b is invertible, then it has a unique inverse. And further, if f of a is equal to b, then a is equal to f inverse b. So an invertible function, if there exists an invertible function, then that inverse function is a unique one. And if f of a is equal to b, symbolically this can be written as a equal to f inverse b. A function f from a to b is invertible if and only if it is one-to-one and onto. Both the necessary and sufficient condition satisfies on this. So if function f from a to b is invertible, then the function is one-to-one and onto, and the vice versa is also true. That is, if the function is one-to-one and onto, then it is invertible. If f from a to b and g from b to c are invertible functions, then g composition f, which is the function from a to c, is also invertible, and the inverse of the composition of function, that is g composition f whole inverse, is given by f inverse composition g inverse. So in this note, we are trying to understand the composition of functions, its inverse. So there are two invertible functions f and g composition f is also a function from a to c, which is also invertible, and it can be proved that g composition f whole inverse is equal to f inverse composition g inverse. Next, suppose A and B are finite sets with cardinality of A equal to cardinality of B, and f is a function from A to B. Then the following statements are equivalent. Firstly, f is one-to-one, f is onto, and f is invertible. So suppose we have two finite sets A and B with cardinality of A equal to cardinality of B, and f is a function defined from A to B, means it is always equivalent that f is one-to-one, f is onto, and f is invertible. So these are some of the points which we need to understand in the invertible functions. Now we can take up problems on these. Let us do problems now. Problems on Invertible functions. Problems on invertible functions. Firstly, suppose f is a function from a to b is invertible, then prove that f has unique inverse. Further, prove that if f of a is equal to b, then a equal to f inverse b. So it is given that f from a to b is invertible function. We need to prove that f has a unique inverse, and also if f of a is equal to b, we have to prove that a equal to b inverse. So let us see the solution. This works as a standard proof. We learned this in one of the note also in the theory. So the same thing, we are going to see the proof of it now. So given f is invertible, given f is invertible, let G be inverse of f. That is G equal to f inverse. Now, from the definition of invertible function, if G is equal to f inverse, then we will be able to write down G composition f is equal to IA and f composition G is equal to IB. This is from the definition of invertible function. Now suppose there is one more inverse for f. Let us assume there is one more inverse for f. Say that is h. Then again by definition we can have h composition f is equal to IA and f composition h is equal to IB. So what we are doing, we are trying to arrive at a contradiction that there is a unique inverse. We have to prove that there exists a unique inverse, means there is only one inverse that exists for f. So in order to prove that, firstly I am assuming G as the inverse of f. Secondly, if at all there exists another inverse for f, say h, then we have to arrive at a contradiction. So there cannot exist two inverses for f, we need to show. So in order to prove that, we now consider H composition of F composition G is equal to H composition F composition G. This is nothing but the associative property. Composition of functions is associative. We have already proved this result. So we are considering this composition of functions and we have to arrive at a contradiction to say that it has unique inverse. So what is F composition G from the definition now? F composition G is nothing but IB. And in the right hand side we have H composition F. We have assumed H composition F as IA. So we will substitute these two in the next step. So this gives us H composition IB is equal to IA composition G. Now, any function, identity function with any other function, composition of those two gives us always the function back. So left hand side is nothing but H, right hand side is G. So we have arrived at a contradiction. There cannot be two inverses. If you observe, H and G are one and the same. We had assumed G as one of the inverse and H as another inverse for F. So we have now arrived at H is equal to G, which means that there cannot exist two inverses for F. There is a unique inverse. So F has unique inverse is the conclusion here. So this becomes a contradiction. So we will be able to conclude that F has unique inverse. So that was the first part of the problem. Now moving ahead to the second part of the problem, we have to consider f of a is equal to b and we have to prove that a equal to f inverse b. We have proved that there is only one inverse, unique inverse now. H and G both are equal, so there exists only one inverse for f. Now it is given from the data that f of a is equal to b. Keeping this, we have to arrive at a equal to f inverse b. So consider f of a is equal to b. We apply function g on both sides. So g of f of a is equal to g of b because g is the inverse of f. This is one and the same as writing g composition f of a is equal to g of b. Left hand side, using the definition of composition of functions, left hand side can be written as g composition f of a, and this in turn is equal to g of b. Now we know g composition f is nothing but ia. We have already assumed that g is the inverse of f and it is already obtained that g composition f is equal to ia from the definition. So left hand side we can write down ia of a is equal to g of b. Identity function on any element gives back the element itself. So left hand side is the element a only. So a is equal to g of b. But what is the function g? G is nothing but the inverse of f. We have already written it. Once we had assumed g as the inverse of f, we have here g equal to f inverse. So I can write down in place of g as f inverse. So this gives us a is equal to f inverse b. So we started with, so this is because of the reason g is equal to f inverse. So we started with f of a is equal to b and we have proved the result that a equal to f inverse b. So that's the second part of the problem. Let us see second problem now. A function f from a to b is invertible if and only if it is one-to-one and onto. So we have to prove that a function f from a to b is invertible if and only if it is one-to-one and onto. So both necessary and the sufficient conditions we have to prove. So let us see the solution. So first, let us assume that f from a to b be a invertible function then there exists a unique function g from b to a such that g composition f is equal to ia and f composition g is equal to ib. So we have assumed or we have used the definition of the invertible function here, but with the word that there exists a unique function. So in the previous proof, we have already seen that there exists a unique function g from B to A such that it satisfies the definition of the invertible, that G composition F is equal to the identity function on A and F composition G is equal to the identity function on B. So assuming F is invertible, now we have to prove that F is one-to-one and onto. So let us prove that one by one. So firstly, to prove F is one-to-one. To prove F is one-to-one, let us take F of A1 is equal to F of A2. Starting with F of A1 is equal to F of A2, we have to prove that the element A1 is equal to A2. This proves F is one-to-one. So we apply the function G on both sides. G of F of A1 is equal to G of F of A2. And using the definition of composition of functions, this can be written as G composition F of A1 is equal to G composition F of A2. Using definition of composition of functions. Now G composition F from the definition is IA. So we can write down this as IA of A1 and the right hand side will be IA of A2. Identity element on any element A1 will be A1 itself and identity element of any element of A2 will be just A2 itself. So we started with F of A1 is equal to F of A2 and we have arrived at A1 is equal to A2. So this proves the result that F is one-to-one. F is one-to-one. Now the second thing we have to prove is F is onto. So keeping F is invertible, we had to prove F is one-to-one and onto. Now let us prove F is onto. F is onto. So in order to prove this, we take any element B belonging to the set B. Then its image G of B belongs to A. And hence we will be able to write down the element B as IB of B. Identity element of any element B can be written as just B itself. So using that property, this can be written as just IB of B. And from the definition, IB is nothing but F composition G. So we can rewrite this as F composition G of B. And this, by the definition of composition of functions, this can be written as F of G of B. F of G of B. So this proves that B is an image of the element G of B which belongs to the set A under the function F, under the mapping F. I repeat, so this proves the result that B is the image of an element G of B which belongs to the set A or the function A under F. We'll write down the same thing. Thus, B is the image. B is the image of an element G of B belonging to A under F. So this proves the result in that F is onto. This implies that F is onto. So maybe to understand this, if I just put the pictorial representation, that will be more clarity. So we have the mapping F. This is set A and this is set B. So we take an element B that belongs to the set B and we find its image in the set A as G of B. G of B. This is under the mapping G. So this proves that B is the image of any element G of B which belongs to the set A. So hence F is onto. Now converse part we have to prove. So converse part we have to prove means assuming that given F is 1 to 1 and onto, we have to prove that F from A to B is invertible. F from A to B is invertible. So in order to prove this, suppose F is 1 to 1 and onto, then it is bijective. From the definition of bijective function, if F is both 1 to 1 and onto, then we say the function F is bijective. So this will help me to understand that, therefore, for every B belonging to the set B, there exists a unique element A belonging to the set A such that F of A is equal to B. So we are trying to grab the definition of the onto function and write down this. So what did we assume? We had that F is 1 to 1 and onto, then it is a bijective function. Since it is a bijective function, we can take any element B belonging to the set B, and there exists a unique element A belonging to the set A such that F of A is equal to B. Now we consider a function G from B to A defined by G of B is equal to A. We assume another function G from B to A defined by G of B is equal to A. We have to prove F is invertible, no? So we need to consider another function obviously from B to A, and we define G of B as A. Then F composition G of B will be equal to, we have to prove F composition G is IB and G composition F is equal to IA. So in order to prove this, we are considering F composition G on the element B is equal to, this can be written using composition of functions F of G of B, and that in turn is equal to F of A, because G of B is nothing but A. So we can write down this as F of A, and F of A we have assumed as B. And this is nothing but IB of B, identity element defined on B. So we started with F composition G of B and we have arrived at IB of B. So this is going to imply for us, and in short we can write down this as F composition G is equal to IB. Now in the same manner we consider G composition F on the element A. G composition F of A. This can be written as G of F of A from the definition of composition of functions, and G of F of A is nothing but B. We have already assumed F of A function as B. So G of B, this can be written now as G of B. And again by definition G of B is nothing but A. So this is equal to A, and this in turn can be written as IA of A, identity element defined on A. So this proves us the result that G composition F of A is equal to IA of A. So for on the element A this is true. So we will be able to conclude G composition F is equal to IA. So we proved F composition G is equal to IB and G composition F is equal to IA. So these two will help us to conclude that F is invertible with G as the inverse. So thus F is an invertible function. F is invertible function with G as its inverse. So this was the proof. It was given that F from A to B, we have to prove it is invertible if and only if it is 1 to 1 and on to. So the necessary part and the sufficiency both we had to prove. So that is the reason we proved first, assuming F is invertible, we first proved F is 1 to 1 and on to, then the converse part. Assuming F is 1 to 1 and on to, we proved F is invertible. Let us see the next problem now. If, third one, if F from A to B and G from B to C are invertible functions, then prove that G composition F from A to C is also invertible and prove that G composition F of whole inverse is equal to F inverse composition G inverse. So we have to prove that G composition F is also an invertible function given F from A to B and G from B to C are invertible. And we also need to prove that G composition F whole inverse is equal to F inverse composition G inverse. Solution. Suppose F and G are invertible functions. Suppose F and G are invertible functions. Then from the previous proof, we can able to write down F and G are 1 to 1 and on to. 1 to 1 and on to. In the previous proof, we have already proved that if F is 1 to 1, if F is invertible function, then F is 1 to 1 and on to. The same is now applicable for other invertible function G also. So from this, we will be able to write down that G composition F is also 1 to 1 and on to. Because F and G are 1 to 1 and on to, the composition of function is also 1 to 1 and on to. Hence, G composition F is invertible. So since G composition F is 1 to 1 and on to, again from the previous proof, if it is 1 to 1 and on to, we can see that it is invertible. So that's the first part of the problem for us. Now, in order to prove G composition F whole inverse is equal to F inverse composition G inverse, we now assume the functions F, G and its inverse functions and prove the problem. We have F is a function from A to B, G is another function from B to C. So G composition F will be a function from A to C. Now we will write down or talk about its inverses. So F inverse will be a function from B to A. G inverse will be a function from C to B. And we have C to A as a function. Its inverse we will assume as, so we have assumed H as the inverse of G composition F, which is denoted as F inverse composition G inverse. and this will be a function from C to A, the reverse of this. So C to A. Now, let us consider the composition of three functions. Consider H composition G composition F is equal to H is nothing but F inverse composition G inverse, and we write down G composition F as it is. So we have considered H composition of G composition of F, that is composition of three functions. We substituted the expression for H we assumed, that is F inverse composition G inverse, we are substituting here. Composition of G composition F we have retained as it is. Now we shall just exchange the brackets and try to rewrite this expression using associative law. So we can write it down as F inverse composition of G inverse composition G, put a bracket for that, and composition F. So this in turn can be written as F inverse composition IB. G inverse composition G can be written as identity element on B, that is IB, composition F as it is. So identity element applied on any other element gives back the element itself. So we have F inverse composition F. And this in turn can be written as IA. So we started with H composition of G composition F, and we have arrived at the result for it as IA. So let us denote this by equation 1. Now in the same manner, we consider another expression, that is G composition F composition H. Consider G composition F composition H, and this can be written as G composition F composition of F inverse composition G inverse. So again I use the value of H that we assumed here. H is nothing but F inverse composition G inverse. So we have assumed it as F inverse composition G inverse. The same is substituted here. Now again the exchange of brackets. So this will fetch us G composition of F composition F inverse composition G inverse. Now again from the definition of identity function, so this can be written as F composition F inverse can be written as IA. So this is G composition IA composition G inverse. Identity element on any other function gives back the function itself. So we have G composition G inverse, and this is nothing but IB. Now from 1 and 2, we will be able to conclude that H is the inverse of G composition F. H enacts as a inverse of G composition F. It is in the same form of the definition of the inverse function. So this becomes like, if at all we have taken H as F inverse composition G inverse, so it behaves as a inverse function now, because we have arrived at the identity function on A as well as identity function on B. So H is behaving as the inverse of G composition F. So thus we will be able to conclude, thus from 1 and 2, thus from 1 and 2, H is the inverse of G composition F. That is, H can be written as G composition F, the whole inverse. But we have already assumed H is equal to F inverse composition G inverse. So on comparison, this can be written as G composition F, the whole inverse, is equal to F inverse composition G inverse. Hence the result for us. We'll see the fourth problem now. Let the set A equal to 1, 2, 3, 4 and f and g, be functions from a to a given by f is equal to 1 4, the ordered pairs are given, 2 1, 3 2, 4 3, and g function is given by 1 2 2 3, 3 4 4 1. Prove that f and g are inverses of each other. F and g are inverses of each other. So given the function f and g and the set A is defined for us as 1 2 3 4, we have to prove that f and g are inverses of each other. So in order to prove this result, first from the given f function, we will be writing down its images. That is, it is given that f of 1 is equal to 4. The ordered pair 1, 4 on the function f can be rewritten in another format as f of 1 is equal to 4. Similarly, f of 2 is equal to 1. F of 3 is equal to 2. And lastly, f of 4 is equal to 3. Similarly, the function g also we will be able to write down. So 1, 2 belongs to g means it is said that 1 is a function related to 2. So we can able to write down that g of 1 is equal to 2, g of 2 is equal to 3, g of 3 is 4 and g of 4 is 1. So by data, first we will write down the same thing. By data, f of 1 is equal to 4, f of 2 is equal to 1, f of 3 is equal to 2, and f of 4 is equal to 3. Similarly, g of 1 is equal to 2, g of 2 is equal to 3, g of 3 is 4, and g of 4 is 1. So this is given in the data. Now we consider G composition f of 1. G composition f of 1 can be written as G of f of 1 by the definition of composition of functions. And f of 1 from the data is 4. So this is G of 4. Again, G of 4 from the data is nothing but 1. And hence this can be written as IA of 1. IA of 1. Similarly, G composition f of 2 we will do it. G of f of 2 from the definition of composition of functions. F of 2 from the data is 1. So we have G of 1. And G of 1 from the data is 2. And this in turn can be written as IA of 2. Identity function on 2. Similarly, for G composition f of 3 we have to do. For every element that belongs to the set A we have to do this. So G composition f of 3 is G of f of 3, which is G of f of 3 from the data is 2 and G of 2 from the data is 3. So this is IA of 3, and G composition f of 4 we are doing now, which is G of f of 4. F of 4 from the data is 3. So we have G of 3, G of 3. G of 3 from the data is 4, and this can be written as IA of 4. So if we observe G composition f of any element that we take, we are getting back the identity function on that element. Same element, if you have taken on 1, we are getting identity function on 1. G composition f of 2, we are getting identity function on 2. Similarly, for all other elements, we have verified that. Now, in the same manner, we have to now consider F composition G. F composition G on 1 is F of G of 1. G of 1 from the data is 2. So we have F of 2. F of 2 from the data is 1. And this can be written as identity function on 1. Similarly, F composition G of 2 is F of G of 2. G of 2 from the data is 3. So we have F of 3. F of 3 from the data is 2. So this is IA on 2. Next, F composition G of 3 is F of G of 3. G of 3 from the data is 4. So we have F of 4. F of 4 from the data is 3. And this can be written as IA of 3. And lastly, F composition G of 4 can be written as F of G of 4. G of 4 from the data is 1. So this is F of 1. F of 1 from the data is 4. So this is IA of 4. So we again here for the function F composition G also we observe F composition function F composition G of any element that we take, we are getting back the same element itself. So that is nothing but the identity function on the same element. So we will just conclude the same thing now. So what have we obtained? For every X belonging to the set A, G composition F of X is equal to identity element on X, and F composition G of X is also identity element on X, identity function of X. So this implies for us that G is the inverse of F and F is the inverse of G. And this can be concluded that F and G are inverses of each other. F and G are inverses of each other. So that's the required proof for us. So we'll see one last problem. Given the function f and g, define them. We have to again prove that they are inverses of each other. So fifth one, let a and b be equal to r, the set of all real numbers, and the functions f defined from a to b and g defined from b to a. These two are defined by f of x is equal to 2x cube minus 1 for every x belonging to a, and g of y is defined as half of y plus 1 whole power 1 by 3 for every y belonging to b. Show that each of f and g is the inverse of the other. So we have to prove that f and g are the inverses of each other. It is given, defined f of x as 2x cube minus 1 for every element x belonging to the set A, and g of y is defined as half of y plus 1 the whole power 1 by 3 for every y belonging to the set B. So let's do the solution. So in order to prove this, we take any x belonging to A first and consider G composition f of x. For any x belonging to A, G composition f of x is given by G of f of x. And f of g of f of x is nothing but, f of x is nothing but defined as y. We'll assume it as y. So where y is equal to f of x. So we get g of y. Assuming f of x as y, we can rewrite this as g of y. And g of y is defined as half of y plus 1 the whole power 1 by 3. Half of y plus 1 the whole power 1 by 3. Now we will substitute for y. Y is nothing but f of x. So substituting that, we can write it as half of 2x cube minus 1, that is nothing but y, which is f of x, plus 1 as it is, the whole power 1 by 3. We observe on simplification minus 1 plus 1 cancel. 2x cube divided by 2 is nothing but 2 getting cancelled. We have x cube. X cube power 1 by 3 will be nothing but x itself. X cube power 1 by 3 will be x itself. So we considered G composition f of x is nothing but x only, and this can be written as IA of x. IA of x. So we will be able to conclude G composition f is equal to IA. Now in the same manner, we take another element y belonging to the set B and we prove the other way. For any y belonging to the set B, f composition G of y is nothing but f of G of y. By the definition of composition of functions, this is f of G of y. Let us assume G of y as, say, z. Z is equal to G of y we have assumed. So we obtain f of z now. If f of x is 2x cube minus 1, f of z can be written as 2z cube minus 1. Now we substitute for z. Z is nothing but G of y. So this can be 2 into G of y the whole cube minus 1. Now substitute for G of y. From the definition, it is half of y plus 1 whole power 1 by 3. So this can be written as 2 times of half of y plus 1 the whole power 1 by 3, and we have G of y whole cube. So power 1 by 3 and cube get cancelled in the next step. So we have 2 into half of y plus 1, 2 into half of y plus 1, and we have minus 1 as it is, which simplifies to y only. Correct? Half and half get cancelled. Y plus 1 minus 1 will give us back y only. So this can be written as IB of y, identity function on the set B of y. So f composition G of y is equal to IB of y. So on the element y, this is true. So this gives us f composition G is equal to IB. So G composition f is IA and f composition G is IB. So we have proved that f and G are inverses of each other. This implies f and G are inverses of each other. So that's the end of the problem. And this is how we work problems on invertible functions. Hope you have followed. Thank you for watching.